Hi, this is David Beasley here. The screencast you're about to watch is from a workshop that I originally presented at the PyCon India conference in October 2019. The original workshop had some audio visual technicalities that actually made recording sort of very difficult. I mean, there's a lot of sort of distortion and artifacts and other things that didn't lead to sort of a very good sort of very good artifact for sort of later viewing. So what I've decided to do is actually re-record kind of the session, do a little bit of live coding, cover the same material here, and hopefully kind of clean it up, make it a little bit easier to watch. So that's what you're going to watch here. As a little bit of background, what the goal of this workshop is to kind of understand the inner working and thinking that goes on in these async frameworks, like asyncio, curio, trio, things like that. But it's very much focused on kind of the underlying kind of programming model, as opposed to a lot of sort of technical details concerning like I/O libraries and other things. So really the goal is kind of to just explore the basic programming model, and also just to kind of get an awareness of why these libraries tend to look kind of complicated. If you've ever looked at the source code for something like asyncio, it can be very intimidating to go in there. And so we're going to try to unravel that a bit. Now, to kind of start off, what I wanted to do is just talk about the fundamental problem that is being addressed in these libraries. And basically, the fundamental problem is one of concurrency. I mean, it's basically about how to do concurrency. So to start off, let me write a couple of functions here. We're gonna be using a couple of functions just to illustrate. So let's say I had a function countdown that just printed out some numbers. I'm gonna have it sleep a little bit, so it runs a little bit slower there. Okay, so let's say you had like a countdown function like that, and then let's say you had a count up function that did something similar. Okay, so while x less than stop, print up x time sleep one, x plus one. Okay, so let's say you had a couple of functions. The programming model that most programmers are familiar with is basically sequential execution. And this is essentially where you would execute like one function and then a function after that. So if you were to structure the code like that, okay, so you have the two functions, you just call them one after the other, you're going to see them just kind of run one at a time. So let's try that over in a separate window here. Okay, so if I run Python example.py, you're going to see the down function kind of operate first, and it's going to run all the way to completion, and then you're going to see the up function run after that. Okay, so that is the programming model that most programmers are familiar with. That's how basically all Python code executes normally. Now, the problem with that is that you often write programs that need to do more than one thing at a time. And the classic example of this are things like network servers. Maybe I'm writing a network service. I need to manage multiple, maybe clients connected to that service at the same time. I can't have it set up where the software just is only talking to one client, and then it does that until the client is done, and then it switches to the next client. Now, I have to be able to do, more than one thing at a time. So that is basically the problem is, how do you do, concurrent execution where you might run both of those functions at once? Now, a classic solution to this, okay, so maybe the easiest and I don't know, most common solution of this is to basically use thread programming. So Python does have a module threading that you can use to launch threads, and essentially what that would look like is you would basically say, okay, well let's launch a thread countdown where the args are 5, and let's start that, and then we'll do another thread, target count up, args is 5. Okay, so you launch 2 threads, and what will happen here is essentially those threads are going to run independently, but concurrently. So if I go over here and run the code again, actually let me comment out my sequential execution here. You will see them going at the same time. You see down and up kind of occurring simultaneously. Sometimes the order is a little bit unpredictable due to kind of scheduling things, but threads basically allow you to do more than one thing at a time. A couple of comments about threads. Threads often get kind of a bad reputation in Python. Sometimes you'll hear people say, you should never use threads, or threads are inefficient, or some other excuse with threads. My one comment on threads is that threads in Python are basically the same as threads in C. Like a Python thread is a fully realized, real operating system thread. It's like a P thread or a POSIX thread. It is the Python interpreter is running kind of fully threaded inside. There's not a lot of kind of extra overhead associated with a Python thread. So using threads in Python is not really, it's not any more resource intensive than it would be in like a C or a C++ program that uses threads. The one real issue with threads concerns the global interpreter lock, and I'm not really going to talk about that here, but Python does have a global lock that prevents threads from running in true parallel, meaning like simultaneous on multiple CPU cores. So threads in Python are actually kind of limited to run on a single CPU core, and because of that, you don't get like a performance benefit from threads. That is probably the real big gripe with threads is that. There are some other facets of threads that are bad, but this isn't really meant to be a thread programming tutorial. But just keep in mind, it's like threads are one way of kind of executing code. Now, the problem that we're going to look at is how would you do concurrency if you didn't have threads? Like, what if you did not have this? Like, you did not have the thread library, and you wanted code to execute concurrently. How do you go about doing that? I guess even before you get into how you would go about doing it, like, why would you want to go about doing it? So the why is kind of an interesting case. I mean, some of the common answers for this is that you might be trying to do or solve like a scaling problem. Threads are sort of great to a point. I mean, you could Python can easily handle hundreds of threads, but you might have a case where you want to write a program where you're handling like thousands of network connections or something, 5,000 network connections. Creating 5,000 threads, maybe that would work on your machine. I mean, you could probably dial the operating system up to do that, but a lot of people would look at that and just say, no, we got to do something else. Okay, we don't want to do 5,000 threads. Another reason for maybe not using threads is just to have a little bit more control over what's happening. Threads do have some downsides, like they're very hard to cancel, for instance. You can't really kill threads after they've been created. I mean, maybe you just want to have a little bit more control over what's happening. So there may be reasons for not using threads. Now the question that comes up is just, how would you do concurrency without threads? Okay, so I'm going to take threads off of the table here. So forget about threads. We're not talking about threads, and we want to run these two functions concurrently. How do we basically do that? Again, not having threads. Okay, so this actually presents kind of an interesting sort of coding challenge. So let me take the code. I'm gonna put this over into another file called asyncio for now. Okay, so I'm gonna put the functions there, and I'm gonna pose this kind of problem. Basically, the problem: how to achieve concurrency, meaning that both functions are going to make progress without doing thread. And here's why this is like tricky. Basically, the issue here is you have to figure out some way to switch between switch back and forth. Basically switching between the tasks. And the question is like, well, how do you How do you do that? And here's kind of the challenge in that. If you look at the functions, they both basically have this inner loop, like a while loop, while n greater than 0, and it sits there and it runs, and while x less than stop. In order for me to switch between tasks, if you will, I've got to figure out some way to interrupt that loop, right? I mean, I have to, if I want these things kind of going at the same time, I can't have this loop just kind of like spinning, because there is no way to kind of interrupt what's going on. So that looping construct, that's we got to get rid of that. We can't do that. Okay, so there cannot be there cannot be looping. But if I can't do looping, what do I like? How do I sequence this kind of stuff? Like, how do I get the things to kind of alternate? So one approach on async is to basically do scheduling of callback functions, or scheduling of function calls. Let me kind of show you how this is going to work. Okay, so what you might do is you would implement like a little scheduler class, and inside the scheduler class, I'm going to make a queue of functions. Okay, so the deck is an object from the collections module. It's basically like a queuing object. Okay, so these are basically functions ready to execute. Okay, so I'm gonna have a little set of functions there, and then what I'll do is I'll give this thing a method call soon, where you give me a function, and all that does is it appends the function to that queue. Okay, so we put a function on the queue, and then I'm going to write a run method. And what this run method is going to do is it's going to sit there and spin, like while there's something ready to run, it will basically pull something off. It'll just pull a function off and call it, and that's it. That's like that's the whole scheduler there. We're basically going to just have this call soon, and this run method. And what we will do in the code is we will basically make like a little scheduler. Okay, so this is something kind of sitting behind the scenes here. We have this scheduler object, and one thing that we can do with the functions here is basically restructure them to interact with that scheduler. So this is going to look really strange, but what I will do is if n is greater than 0, I'm going to print down n, I'm going to sleep, and then instead of looping here, I'm going to go to the scheduler and I'm going to basically say, well, call soon lambda countdown n minus 1. The presence of the lambda there, by the way, is to make a 0 argument function. If you look up at the scheduler code, it's been written in this super minimal way where it's just you give me a function and I just call it with no argument. Like every function has no argument. So what I've got here is I have a no argument function that calls countdown with a decreased count there. So I'm gonna rewrite kind of countdown like that. Here's what this would look like. Let me just kind of run that real quick. Just to show you what that would look like. What I could do is I could say schedule call soon lambda countdown 5, for instance, and then I could say schedule run. You will actually find the thing actually runs the countdown method. Let's actually try that. See, okay, down 5, 4, 3, 2, 1. Okay, so it definitely works. It looks a little weird. I mean, it's like basically what you're doing is you're implementing a recursive function call, but it's involving this like backing scheduler. Okay, this kind of scheduler behind the scenes. So if n is greater than 0, we do the step. We do this call soon thing. We can do a similar kind of structuring for the count up function. So the way that this is going to work is we would have to basically say, well, if x is less than stop, will print up, and then we have to do a call soon with some kind of function that takes us to the next step. This actually presents kind of an interesting problem, like more of a code structuring problem concerning this x variable. X is actually something that's kind of like it's like internal state basically, and I need to figure out some way to maybe carry that along. There's a couple of different ways you could do that. One is you could make it a default argument. I'm not super happy with that, but let's roll with it for a second. So I mean, you could make it a default argument, and then you do a recursive call where you increment the argument. That might be one way to do that. Here's what this would look like with the scheduler now. Okay, so you do scheduler call soon, lambda countdown 5, and then you do scheduler call soon, lambda count up 5, like that, and then scheduler run. If this is working right, you will kind of see these things kind of alternating and progressing through their code. Let's try that. Okay, so you see them running. Let's see. I used the wrong function name. Pardon me on that. Okay, count up, stop, x plus 1. Let's try that again. Expect to see some errors during this session. I mean, I'm kind of live coding it. We'll probably make some mistakes. I'm not gonna edit those out. So, I mean, I'll fix the mistake, but I'm not gonna edit the recording. So, so now you see the thing kind of alternating. And again, what makes this work is that I have restructured the functions so that they basically always just return. I mean, so like the idea on a function is it will do something, and then it will immediately return from the function. But when it returns from the function, it might schedule kind of like a next step of the calculation. It would say, well, you know, the next time I want to do something, call myself with like a decreased argument or some other thing. So effectively, it's kind of the same as a while loop. Maybe it's a funny kind of while loop. It's just that the looping is kind of being coordinated with this kind of backing scheduler. If you don't like that default argument hack, by the way, one way to fix that is to maybe write like I don't know, like an internal function of some kind, like like a run function where you pass in like the x as an argument, like that, and then you take your code and you kind of put it inside this function. Okay, so you pass the argument, and then you basically run that. Like you would say, okay, well, okay, recursively call run, like that, and then inside your function you would kick it off with run 0. I think that will solve that problem. Although taking that approach, it's kind of like your job security might be going up a bit there, having a nested function and then calls to the nested function. But that's an alternate way of doing that. Okay, so this is kind of giving you the start of one of these frameworks. Basically, you can if you want to do concurrency, and again without threads, one way to do that is to do this kind of function scheduling idea. Every function just kind of falls off the end, and it has the option of scheduling another function call later on. All right. Now, as an extra twist on this, I want to talk about this time sleep function for a second. Okay, so I left that in the code, and it turns out that the sleeping presents kind of an interesting problem here. Like what if this first sleep was changed to like sleep 4? Like, so countdown is basically going to sleep 4 seconds between each step, and count up is going to sleep 1 second between each step. Okay, you kind of see what's going on there. One question is just what would you expect the output to be from that? Or what would you like the output to be? If I were to run that right now, what you're going to see is it's going to do down 5, and it's going to sit there for 4 seconds. It'll do up, and then it's going to do down 4 for 4 seconds, and then up runs real fast. Essentially, that time sleep is basically blocking everything else from making progress. Okay, so that time sleep is basically it's like a blocking call, and nothing else can happen when it's sleeping, because it's like the scheduler is kind of frozen and so forth. If that is something that you wanted to fix, you'd have to think about some way to not do that time sleep. Like you'd have to come up with some alternative approach, and one possible way to do that. Okay, so let's say you didn't want to do that. Okay, you don't want the time sleep. One way to do it is to maybe put that functionality in the scheduler. Like you could come up with a method like call later, where you give it like a time delay. So you change your code where it's like, okay, call later, like 4 seconds from now, I want you to call this countdown n-1. Here, call later 1. It's like 1 second from now, I want you to call the run method. This is essentially taking like the management of time and putting it into the scheduler. And this is something that most of these, all of these async frameworks usually have to deal with, is some notion of time management. Like they would have like a call later function where you have a delay and some function, and then you would have to organize or coordinate basically the manage of that delay. Here's how you might manage that. Basically, to manage the delay, you might have a separate list of kind of sleeping functions, if you will. Okay, so you have your sleeping functions, and what you would do to manage the sleeping functions is you would figure out kind of like a deadline. Like you would say, okay, well, the deadline for this call later is going to be the current time plus the delay. This is kind of like the expiration time, basically. You're sort of saying, okay, 4 seconds from now is when this function needs to be called. And then what you would do is essentially put that deadline along with that function into that sleeping queue. Okay, so you're gonna record kind of like a record, sort of saying, okay, when is this function going to wake up? And then when is it, basically when is the, like, what is the deadline and when is it going to wake up? Okay, so you're going to put that there, and then what you would have to do in the run method is you would need to have some kind of coordination of that sleeping list, basically. So if you had something ready to run, you would just run it right away. If you don't have anything ready, let me change this. If you don't have anything ready, you would basically have to sleep. So let me kind of restructure this a little bit. Okay, so while there's something ready or there's something sleeping, if there was nothing ready to run, what you would have to do is basically find like the nearest deadline. Okay, so you're gonna find the nearest deadline. One way to do that is to store the deadlines in some kind of sorted order. I'm going to give you a better solution for this in a second, but one way you might do that is you might like sort by kind of closest deadline, like that. And so you would come in here and you would say, okay, deadline funct is equal to self-sleeping, pop 0 or something. And then you would find out like how many seconds it is between now and the deadline. And then if the delta was greater than 0, you would sleep. Okay, so what would happen is you're basically gonna look at that deadline, sort of saying, hey, what is the next deadline? I'll sleep for that long, and then when I'm done with that, I'll put the function into the ready thing. And then we'll run ready functions. Okay, so we're taking the scheduler, basically adding like a little bit of like time management into it, where we're kind of looking for the next deadline. We'll pop that off, sleep for that amount of time, put the function in the ready area, and then run stuff while we still can there. Okay, so a little change there. What will happen with this code is that you'll see basically the proper time sequencing. I mean, what we expect to see here is that this code is going to go down, and then it will go up, like up, 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 and then down, up, 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 down, up, up. You know, because basically the up is running much faster than the down. Let me just put a few different arguments in here and try that. So let's try running that. Okay, so now you see down 5, and it's like up 1, 2, 3, 4, like up 0, 1, 2, 3. That's exactly the behavior that we want. I mean, essentially the down was running much slower than the up, and now we're getting that. So this actually gives you kind of a, you know, actually a major piece of some of these async frameworks is that, you know, not only do they have, you know, this idea of like scheduling of functions, but they also might have to do some things like time management and delays and other, you know, other kinds of things here. So that's you know, another kind of, you know, another thing you're going to find. One typical implementation detail, by the way, is that if you're gonna sort things by a deadline, you're basically creating what's known as a priority queue. You're inserting things where the priority is basically where the next deadline is. There is a Python module for doing priority queues, which is the heap queue module. That's maybe a little bit obscure, but what you might do instead is you would do heap queue, like heap push, self sleep, deadline function, like that. That will basically put the data into that list, but it will maintain it in an order that's basically prioritized by deadline there. And then when, instead of popping off the first thing there, you can do heap queue. I think it's like heap pop. That will sort of save you the problem of having to do sorting and other stuff. Also the like the use of a heap or a priority queue is sort of much more efficient than that technique that I was doing before. Like it's not really efficient to have to sort the whole list of sleeping functions every single time I insert something in there. So pretty standard technique is you know, to see the heap queue module being used. All right, and again, we have this kind of sleeping behavior going on here. One other technicality with this, turns out that there are some corner cases that one has to worry about. One corner case concerns the ordering of two different functions with the same deadline. Like let's say you had two different functions. Like let's say you had a function f and a function g, and then let's say you had a like a sleeping list like this. Like, okay, sleeping is equal to like 2f, and then another one like 2g, like that. It's like same deadline, two functions. It turns out that presents some problems with ordering. Like if you tried to do a sort on that, you'll find that it breaks because you can't do like a less than or a greater than comparison between functions. No, this is actually a really interesting corner case. It is technically possible that you could have two different functions that get scheduled with the same deadline. It might be rare. It might almost never happen, but like every now and then, you could get two functions with the same deadline, and then all of a sudden your program's going to crash with this like this type error, basically saying you can't do comparison between function and function because they've got the same deadline and they can't compare. That is extremely annoying to debug, by the way, because it would happen very infrequently. So one little extra kind of tweak that you see on these implementations is that they will often incorporate a sequence number, just an ever increasing sequence number, and what they would do is update the sequence number. Okay, so sequence plus equal 1, and then they would include the sequence number in the in kind of the priority queue. So they would sort of say at this deadline and this sequence number, call this function. The idea on the sequence number is to do tie breaking. Like if two functions had the same deadline, the sequence number will basically break the tie and avoid that kind of comparison between functions. So that's a technique that you sometimes see as well. And that's actually typical of a lot of these libraries. There are a number of kind of like tricky corner cases like that you have to worry about. That happens to be one of them. All right, so just as a quick review, we've got the scheduler. It is essentially executing functions one after the other. Okay, so it's just executing these like 0 argument functions. It additionally has this support for sleeping, and then if you want to do concurrency, you have to basically interact with that scheduler. So you have a countdown and a count up function. Those functions do not do any kind of looping or anything. It's just like they basically run, and they immediately end by scheduling some later calculation. So like nothing in here like blocks or anything. It's just if n greater than 1, we'll print 0. We'll print it the down n, and then we just immediately schedule like a later operation. And the same thing for count up. And it's that structure of just immediately returning from the function and scheduling something that allows you to get kind of concurrency here. We're doing that because we're trying to not do thread programming. All right, so that's a starting point. Now, using this as a model, it is possible to do other kinds of problems. One problem that I wanted to look at. Okay, so let's set that aside for a moment. One very classic concurrency problem is something known as the like a producer-consumer problem. And let me give you kind of this scenario on a producer-consumer problem. This is essentially a problem that typically involves queues. What you do is you might have like a producer function, like this, where you would carry out some kind of loop, and maybe push things into a queue. I think I'm going to call it just queue there. Okay, so what you would do is you would say something like producing and you would put something into a queue like that. Okay, so you're producing a bunch of data. Maybe you put like a none on the queue. This is kind of like a sentinel value. Do some kind of shutdown, and then you would have a consumer that's sort of picking these up. So what the consumer code would look like is you would get something from the queue. If item is none, that means you're shutting down. Okay, so you'd have code like this. Basically two functions. One is producing data into a queue. The other is consuming data from a queue. And then you would have these two functions maybe running concurrently with threads or something. I'm doing kind of like a classic kind of solution here with threads and queuing. So what it would look like is you'd basically make a queue. Like here's my queue. Okay, thread safe queue. And then you would launch these two things. So you would say, okay, thread is equal to producer, args is queue10. Okay, let's start that. And then you would have the consumer, args is queue start. And if I've done this right, you'll see like the producer kind of producing things and putting them in the consumer. I'm actually one other thing I want to do here is I want to slow it down a little bit by just having the producer sleep like that. Okay, so let's try to run that. Okay, let me try this out here. Okay, Python producer.py. Okay, so what you're going to see is basically the producing message, and then you'd see the consuming message, and you're seeing a handoff of data from one to the other. Okay, so this is a kind of a classic consumer producer problem involving threads. This is actually a really great way to program with threads, by the way, is to coordinate communication between tasks using a queue. Now, the problem that I'm going to pose is how would you do this without threads? No, so let me write this to a file. I'll call this a producer for the kind of the async version of this. And the challenge is how to implement the same functionality but no thread. How would you do that? So we're not allowed to use any of the queuing module, we're not allowed to use the threading module, anything like that. Instead, we have to use this this scheduler that we've made. And a big part of the problem actually concerns this, like that get method. Essentially, get is this function on a queue that is supposed to wait until something shows up. Okay, so the whole idea on queuing is the consumer is just supposed to sort of hang around, wait for something to happen, and then when it does happen, it's supposed to run. And the question is, how do we implement the waiting? It's kind of an interesting problem. So let's talk about the strategy here for a second. So the first thing is that we're going to use the same scheduler that we had before. Okay, so this like little scheduler thing that we wrote here, we're gonna use that. I'm actually going to just copy that code into this other file so that we can work with it. So let's keep that up there. Okay, so that is the code that we're going to work with. I'm going to try to keep that code more or less unmodified. Okay, so I'm going to keep that code around, but the real question is just how do I need to structure this stuff to not use threads? I mean, I cannot use threads. I mean, there's a whole point of async is that I'm not going to use threads. So forget about this threading stuff. And I also am not going to use this thread safe queue. So to make that work, I'm going to have to implement kind of my own queuing object of some kind. I mean, I'll have to make like a special object. The way that you make a queue is you're gonna have like the items being queued, like that. I'm gonna have a put method that puts something onto items. Okay, so we have that. But then we have this get method that has to wait, basically. I mean, so wait until an item is available, and then return it. The question is, how are you going to do that? It seems really kind of weird. Like like how would you actually do that? So keep in mind that the waiting is basically a problem because the whole idea in async is that you're not supposed to wait for stuff. Like you're not allowed to write code that just sits there in a loop or prevents other things from happening. So I have to figure out, some programming model to make this work. Like how would you do it not waiting? Well, here's really the only kind of the only technique that I can think of here. One way to make that work is you would provide a callback function in get, and you would use that. You would basically say, well, okay, if items are available, like if there is something in items, what we will do is basically fire the callback method with one of the items. Okay, we'll say, okay, if there's an item available, we'll just call you and tell you what the item is, like that. But if there's not an item available, I mean, and this is the tricky case. Like, what if there's nothing available? Then I have to somehow kind of just suspend myself. I have to walk away and just say, well, I can't do it right now. So in order to implement that, what you will often do is make maybe a waiting queue like this. Okay, so this is all getters kind of waiting for data. Okay, so we would make like a queue like that, and maybe what we would do is we would just put like a function in there. We would say, okay, well, I'll put something in the waiting area where I'll call get. I don't know. Maybe I'll just do call the get again. Okay, just append that. And so what happens here is if no data is available, we just append ourselves to this waiting thing, and then we just walk away. So the get method just immediately returns, doesn't stop, doesn't loop or anything like that. And we would have to have something in the put to basically deal with that later on. Like what would happen in the put here is if there was something in the waiting area, we would have to arrange to call that. Like we would basically pop something out of the waiting queue, and then maybe we would call it. Now this actually presents kind of another interesting kind of weird problem. Do you call it right away? Like, do you do this? Or do you do something else? Turns out that in a lot of these kind of async frameworks, what they will do instead is basically interact with the scheduler. They'll essentially go to the scheduler and they'll say, okay, scheduler, I want you to call soon this function that I popped off. Part of the reason for that is to try and avoid getting into sort of like deep recursive kinds of functions. I mean, if I were to directly call function here, that could end up creating kind of like a very deep chain of like kind of nested function calls and other sorts of things. I'm really trying to kind of avoid that. So what's going to happen is basically with the put, you would put something on the queue. If there's something waiting, you pop it off and you just give it to the scheduler saying, hey, run this thing when you get around to it. And then we just return right away. Very kind of mind bending. Okay, so there's our queue implementation. How you're going to have to code with this, by the way, is also kind of interesting. So in order to code with this, keep in mind that we cannot do things like for loops. We can't do a for loop there because the for loop is going to prevent this this async scheduler from switching tasks. I don't want that. That is not what I want. So I'm going to use kind of the same technique that I had before. I'm gonna give this kind of a run method where you give me the n. I'm going to say producing n, where I do a q put on n, and then I'm going to do something with the scheduler, basically call later. 1 second from now, I want you to call later this run method with n plus 1. And then I'm going to kick the thing off with a run 0 there. Again, that looks pretty strange, but and then this part where it's done down here. You'll shut down the queue there. Okay, got to take a moment to study that. I mean, again, what's happening is this run method, it essentially just does a check, does the thing, and then it immediately falls off the end of the function. There's no looping here or anything to kind of, keep it, tied up. The consumer code is going to also be a little interesting. I mean, there's going to be maybe an internal function consume. Actually, do we need a... Maybe we don't need an internal function there. Actually, what we would do... No, actually, we do need an internal function, I think. What we would do is have like a consume function where you give me the item. Okay, so... So if item is none, we're just going to do nothing. And then if it's not none, what we will do is basically come in here and say, okay, consuming item. And we will call ourselves recursively here. And then we're going to do a qget. And for the callback function, I have to look at this. Yeah, I think. Oh, yeah. Okay. No, I think we're okay. Okay. It's already making my head explode. Okay. So we're going to do, qget, and then the callback is basically going to be this consume item. Very brain-bending kind of thing. So what the idea is we'll do this qget. If there's an item immediately available, you'll see it print out, but otherwise it's going to suspend itself, and then it'll get called back later on. Okay, so let's make an async queue object. We're going to do schedule, call soon producer. Q10. Okay, so we're gonna do that, and then we're gonna do a call soon on the consumer of Q, and then we're gonna run the thing. If I've done this right, and famous last words, you should see it kind of behaving the same as the threaded version. I called this a producer, so let's give it a shot. Okay, so you see it running the the same way as before. Okay, producer consumer done, but it is definitely a very tricky interaction here. The functions basically have to be written so that there's no blocking, there's no looping or anything like that. So, the producer and the consumer, they essentially do kind of one step, and they immediately kind of schedule a function to run next. They're interacting with the scheduler. Same thing with the consumer down here. You do a get, and then you have to pass a callback in for the thing to execute when you got an item. And then the queue class itself needs to do a little bit of kind of management of waiters. So it has its own kind of like little internal queue, and there's kind of coordination between the put and the get going on there. So what happens is the get will trigger a callback if there's data available, and if not, then it has to arrange for itself to execute later. So the idea is, if there's no data, it just delays the method to happen at a later point in time. Pretty tricky kind of thing going on there. All right, so in this async queue, you already see a fairly tricky interaction between the get and the put. I mean, essentially the get has this callback function that gets provided to it, and all of the results of the get communicated through that callback, right? It's like that is the thing that's kind of triggering the, when something happens, you sort of trigger that. So I wanted to make one modification to the queue that's going to make this it's going to make it significantly worse, but it's going to illustrate kind of a problem that comes up. The change that I'm going to make is I'm going to give the queue an internal flag that determines whether the queue can be used anymore. And the purpose of that flag is it will basically prevent you from putting new items in there. So if the queue is closed, I'm going to raise like an exception. I'll say queue closed, can't do that. And I'll give this thing a close method that basically flips that. And the idea on the close is a producer would use that instead of this weird hack with the none object. So instead of putting none on there, when you were done producing, you would just come in and say queue close. And that basically means like no more items will be produced. Okay. So this is the idea. The producer is going to put things into the queue. It's going to close the queue, and then when it's closed, nothing else can happen. Now, here's where this gets kind of hairy. How does the closed queue interact with this get function? Like, what is the proper interaction there? And here's why this gets really sort of kind of weird. Okay, so first of all, if the queue still has items in it, so let's say the producer produces a bunch of items, produce 1, 2, 3, 4, 5, 6. You produce a bunch of items. If those items are still in the queue, then it should be okay to call get. Like if somebody calls get, you want to pull out the items basically because it might be the case the consumer and the producer are running at different rates or something like that. The idea on the close is that you don't want to lose data. You just don't want to. You're just saying I'm not going to produce anymore after that. So if there's items available, you're still going to do the callback. Okay, so this is still runs, if closed. But where the closed is going to kind of manifest itself is in this case where there's no more items. Okay, so no items available. Okay, so must wait. That is basically where you're going to do like the closing thing. And so the question though is how does that get communicated like how does it get communicated back? Okay. So if the thing is like if it's closed, what do you do here? Okay, so how do you communicate it? Now this is why this is actually kind of tricky. It turns out that the result of the get is basically this callback function, right? I mean, essentially the way that the queue works is you call get, you're supposed to give it this callback, and it's the callback that's supposed to sort of determine what happens now, like what is the next step of the calculation, and it seems like that callback is basically what needs to deal with the queue being closed. Like here, if you look at the consumer code, this is basically my callback. It's like I got the item is none, consumer done, consuming item. This thing here, this none check, this is basically the queue closed check there. So the place where this is being checked is kind of put in the callback function. And the question is like, how do you communicate an error in that spot? I mean, now this is a really tricky kind of coordination problem that takes place where I have to basically communicate an error to the callback. I either have to have like a result going into the callback, or I have to have like an error. I'm not sure whether that problem is making sense, but you know, this is basically an error state, and this is like a regular result. It's kind of bizarre. So here's one of the ways that problem might be addressed. You're probably gonna hate this, but so one way that this might be addressed is you would create a special result class. And the result class is basically going to have a value, which could be none, or it could have an exception. It could be none. Okay, it could have a value or an exception. Okay, so let's see you do that. And I will basically provide a function that returns the result. And the way that this function will work is it'll basically say if there's an exception, it will raise it. And if there's not an exception, it will return the value that got passed in there. Okay, this looks a little strange, but essentially what you've got is you're packaging either a value or a Python exception into an object. So it either worked or it didn't work. And that is the kind of thing that you're going to use with the get method down here. It turns out that this, like, instead of calling the callback where you just give it the item, what you would do is you would pass in a result. Like you would say, okay, the result value is basically this pop left thing. Okay, that is basically that's like a good result. Okay, so you're gonna do that. If the thing is closed, what you're going to do is you're going to do the callback function, and you're going to pass in an exception instead. You'd basically say, okay, let's call the callback, but let's pass it a result where we basically indicate that the queue is closed. Okay, this is an error result. We essentially have two possibilities coming back. It's like you either have the good result or you have the bad result. And so we're gonna set that up with basically the callback there. And then in the code that uses the callback, you would have to basically check this by kind of unwrapping the result, if you will. So what you would do is you do a try, and you would say item is equal to, I don't know, result.result. Okay, that looks really bad, but I apologize for that. But you would say result.result, and then if it worked, you would just continue with, your your regular code that you had before. Okay, so you'd have that. And then if it had queue closed, you could do consumer done. So it's kind of a way of sort of communicating, kind of a, kind of a like an answer along with a, like an exception like that. Basically, you're putting it inside of an object and passing both things along. So the code is already getting like way more complicated, where you have the result, you have the value, and so forth. Let's see if this actually works. So the idea now is the producer is going to produce things. It's going to close the queue. That closing of the queue is going to manifest itself in the consumer as a queue closed exception, but only after all the items have been consumed. Let's try it out. Okay, so the code seems to be running the same as it did before. Producer done. Did not see the consumer done method, so let me make sure that yeah, kind of wonder what happened with that. Except queue close. Yeah, I'm not sure what happened with that. You have to. The consumer definitely appears to have stopped, but the question is, why wasn't the message printed? That's a very interesting kind of problem there. Let's take a take another look at that. Okay, if there's items, we'll do the callback. Oh, I think I know what it might be. I think I might know what's wrong there. Okay, so it's kind of did like a weird like scheduling there. Let me try that. Try that again here. No, it's still no consumer done here. The idea is that in the get, if there's items available, we immediately call the callback. If it's closed, we'll do the callback with an error result. Oh, I know what I think I know what it might be. If you close the thing, and there happens to be something in the waiting. There's no items available. Let's do that. You would have to basically schedule their callbacks. Let's try that. Okay. Well, it did make further progress on it. Let's see. Am I missing an exception somewhere? Did I actually define that? Oh, maybe. Yeah. Okay. Good. I did not actually define my queue closed exception. It's making progress though, so at least I got the error that time. Ah, okay, it's exactly what I wanted. Now, one comment on why I did this last little part is it turns out that error reporting is actually a really tricky problem in these async function like these async frameworks. If you're using like a lot of callback functions and you need to communicate errors, you do end up with this problem of how do you carry errors around in your program. Putting them inside of an object like this is one way to do that. Turns out that asyncio kind of does this by packaging everything into a future object. So futures kind of serve the same purpose as this result. You might see different variations of this used in libraries, but essentially it is addressing this problem that there's a notion of success and there's a notion of failure, and you have to kind of communicate that in the system. The other kind of just general comment is you really are seeing how this turns into kind of callback hell, if you will. I mean, so that's a term that you often hear people throwing around where it's like, oh yeah, I have callback hell. You're really seeing that here. I mean, it's like the code is just turning into this like spaghetti of callback functions. I frankly find it very hard to kind of wrap my brain around what's happening, but it's all kind of going back to this core scheduler where the only thing that it knows how to do is basically execute a function, and then it has like scheduling a function. So this is one style of kind of async programming is basically that, and it's really, again, it all goes back to this fact, like if you're not going to use threads, then you have to figure out some way to switch between tasks. And one way to switch between tasks is essentially to organize things so that you are just working with these little tiny callback functions that just do one thing and they immediately return. You're never allowed to do anything like while loops or for loops or blocking or anything like that. It does lead to a very kind of convoluted programming style. In the next part, we're going to see, kind of an alternative approach to this, but this is one approach for solving the problem. All right, in this next part, we're going to reset back to the beginning. So keep in mind that our original goal is to do concurrent execution of tasks. When we started the workshop, I had these two functions, count down, count up. I wanted those to run concurrently. Thread programming is one way to do that, but if you're not going to use threads, you have to figure out some kind of alternative approach. One alternative approach was this whole scheme with callback functions. Basically, you structure the code so that you do not have while loops, and then you sort of schedule function calls. Just to refresh your memory on that, it sort of led to code that kind of looked like this. Basically, you had functions where you're interacting with a scheduler, and you're doing kind of this kind of recursive function calling and other things. The big problem with that code is that it leads to this kind of like tangled mess of callback functions, and nobody can understand what it's doing. So another approach for doing this is, instead of doing callback functions, you might use Python generators instead. So I'm going to make a new file here. Okay, hold on. Okay. I'm going to take my example file here. I'm going to make a new library. I'm going to call it Yieldo. I don't know. Why not? Yieldo is a good name. Okay, so what we're going to do in Yieldo here is, instead of like just falling off the end, I'm going to put a yield statement in the function. This is effectively turning these functions into what are known as a generator function. Just as a little background on generators, typically generators are used to implement iteration. what you would do is you might write a function while countdown n, while n greater than 0, yield n minus 1, like that. And what you would do is use that to feed a for loop. Like you would say for x in countdown 5, print, t minus x or something. This is by far the most common use of yield, is basically iteration. You're using it to feed, feed for loops. But one of the features of yield is it does cause the function to basically stop. I mean, when you use yield, you get this generator object. If you call next on it, it sort of runs one step of the calculation, and then it stops. You call next again, and it stops. So the fact that the function kind of stops midstream like that gives you an opportunity to also do concurrency. I mean, so one option is that you write your functions, you put yield in there, and you're going to do the same kind of scheduling thing that you had before. I mean, so this code is going to be almost identical to what we just did in the first part with callback functions. Okay, so we're going to have a scheduler. We're going to have queue of ready things to run. But what we're gonna have in here is we're gonna have like a little run loop. So while ready, where we get like the the current thing. Okay, so we're gonna do self.ready pop left. And then what we're going to do is drive it as a generator. So we'll do next.self.current like this. And then if you get a stop iteration, you just kind of forget about it. Okay, so you're gonna do like a little trick like that. The other thing that we're gonna do here is that if self.current is still around afterwards, I'm gonna put it back on the ready queue. There's something subtle about that we'll get to in a second, but essentially what has happened is this is operating as kind of a little round robin kind of scheduler here. Okay, currently executing generator. Okay, so we have a run method like that. The only other thing I'll give it is kind of a new task method, perhaps, where you give me a generator and put it onto the queue. Okay, so the code here, it's almost the same as the callback code. I mean, the only difference is that we're not executing callbacks. What we're doing is advancing a generator kind of one step, and that is the mechanism for driving the code. Okay, so we'll write a little scheduler like that. Again, we have to have this thing kind of running in the background. Okay, so this is this kind of background, scheduler object that we have to interact with. We've got our code with the yield statements in there. And here's how this thing will run. We'll basically say, okay, schedule new task, countdown 5, for instance. Schedule new task, count up 5. And then we'll do schedule run like that. And again, this mirrors what we did with the callback functions. Like the structure is virtually identical, and all the pieces are almost identical. There's a queue, there's appending, there's popping. It's really just this driving as the generator, which is different about it. Okay, let's try running that and see what happens here. Okay, yield though. Okay, so you see the thing kind of switching back and forth. All right, switching back and forth. Now, the thing that's kind of awesome about that, and it's subtle, but it's awesome, is that it allows you to switch between these functions without having to kind of do weird things with like these callbacks, right? I mean, I didn't have to write like a helper function. I'm not doing weird recursion or anything like that. The code basically reads in just like a straight sequential manner, except for the presence of the yield statement. It just kind of does one step at a time there. That is really the appeal of it, is that you can write this kind of sequential code. It's just driven in a different way. Now, there is a complaint about it, though. One of the complaints is that it does seem to be kind of an abuse of the yield statement. Normally, yield in Python is probably thought of for like iteration. Like that is by far the more common use of the yield statement, is to write things to feed the for loop. And we're not really doing anything with the for loop here. I mean, we are doing a completely different kind of execution, or a different thing. And in some sense, it's kind of a hack that we've layered this on top of generator functions. And I mean, it's a neat hack, but it's I don't know, it's kind of sneaky. So the use of the yield, a lot of people look at that and it's like, I don't know, couldn't there be something better there? So one of the things that has happened in kind of modern Python versions is that some steps have been made to kind of hide the yield statement. Basically, there's been an acknowledgement that the use of a generator for concurrency problems is kind of interesting all on its own, and so there have actually been some syntactic improvements in Python, and some sneaky tricks that you can play to kind of hide that detail. So let me kind of show you the neat trick here. One of the tricks that you can do is you can provide a class. You can make a class called awaitable, or you can make an object. And in this object, you can give it a magic await statement. You're like, okay, interesting. And in the await method, the only thing that needs to be in there is a yield statement. It has to appear somewhere in there. Okay, so you can have a yield statement in there. And then what you can do is write a function, perhaps, that returns one of these awaitable objects. Like I can say, okay, switch, return awaitable. You're looking at that saying, well, okay, that's pretty weird. What is happening there? What is happening there is it allows you to basically hide the yield statement. Instead of just having yields, you can now use this new Python statement, like the await statement. You can write code like this, where you'd say like await switch, and the idea is that you're going to switch tasks there. Okay, so you say await switch, await switch. Okay, again, like switch task, and you're effectively hiding the fact that there's a yield sitting there. In some sense, you're sort of taking, this is the approach that Python takes with all of its kind of magic methods, right? I mean, like if you add two numbers together, there's a magic method add that takes care of that. Or if you're accessing the items in a list or something, there's a magic method get item that maps onto that. Essentially, await in Python is a new language feature, got added in Python 3.5, and it is tied to a magic method await. Kind of like the rest of Python, how the rest of Python works. So there's like a hook for basically customizing that. One little detail about the await is it turns out you can only use that if you're inside of a function that is also declared to be an async function. Now, this is absolutely critical, actually. Like await is only enabled if you also have a function declared as async. Okay, so you have to declare both of these things as async. Very subtle kind of syntax change, but you use async, and then you're going to use await. The only other change is that if you're going to use async and await, you can no longer use next. Instead, what you have to do is you have to say self.send, where you send a value to a coroutine. It turns out that these async functions create what are known as coroutines. This is a little terminology change, but basically they're generators. Okay, so you have like a new task coroutine, self current, pop left, and so forth. And this code will run the same way that it did before. Famous last words. Let's try it out here. Okay, run yieldo. It's basically cycling through the task. It's the same thing that we did with generators. What we have really done though is kind of abstracted the yield away. We have totally hidden that fact that there's a yield statement. Essentially, the user of this thing, they just see async, they see await, they see the switch. They have no idea what's going on in the switch. Something happens. We don't know what. We just know that it switches tasks. Somehow, the fact that a yield involved is kind of an implementation detail. It's like nothing to see here. Kind of look away in there. So, just as an aside, if you do see async and await being used in Python, if you follow the chain of function calls down far enough, eventually you will hit a yield statement. You might have to dig very deep to find it, but if you keep just kind of following the chain of execution, eventually you're going to see that. So async and await, they're basically hiding the presence of a yield statement somewhere. Might be hard to find, but somewhere in there there's a yield statement. Now using that, it turns out that you can build up the rest of the features that you use in kind of standard async framework. One of the things that we did in the last section is we addressed this problem of time. How do you do, how would you do the sleeping? Like I had this one example where you had the countdown was running sleeping 4 seconds and the count up was sleeping every 1 second. And then we kind of showed that the up was running 4 times faster than the down. I don't know whether you remember that or not. Question is well, how would you implement something like that? It turns out that you can implement it almost entirely just using this this switch function that I wrote. I mean, this might blow your mind a little bit, but well, here's how you could implement that. We're going to go to the scheduler, and we're going to give it a list of sleeping tasks. That is exactly the same as what we did in the last code with the callback functions. I mean, I don't know if you remember that, but we had a list of sleeping things. What I'm going to do on the scheduler to manage that is I'm going to give it a method async def sleep where you give me a delay. Now the idea here is that basically the current task or the current coroutine wants to sleep. And the question is well, how would it do that exactly? Well, the way that you're going to do that, okay, let's figure out the deadline. So the deadline is going to be time right now plus whatever the delay is. I think there was also that weird sequence number thing. I mean, this is something that we had before. So we'll bump up the sequence number. What we'll do is we will basically push onto the heap the deadline, the sequence number, and the current coroutine. Okay, so we're going to push that onto the heap, and after we do that, we're going to set the current to basically none. We're sort of saying, okay, so here's the idea. I'm a coroutine. I'm running. I want to sleep. I'm going to figure out what my deadline is. I'm going to put myself on this sleeping queue. I'm going to set the current running thing to none. And then I'm going to await switch. Switch task. Kind of got me here. Got to figure out what's going on here. Okay, so the idea, I'm going to put myself to sleep. I'm going to tell it that there's nothing running right now, and then I'm going to switch tasks. What's going to happen with that is that this bit of code here, this thing that's driving the generator, it is basically going to run this send method. It's going to come back and it's going to say, well, there's like the current task is gone. It's like it's gone because it got set to none up here at the top, right? I mean, it's like, okay, not gone. It's not around anymore. So I'm just going to forget about it, and then I'll go get another task. Okay, kind of a sneaky little trick here. I'm going to do a similar thing that I did in the other code. Basically, the outer loop here needs to run like while something is ready or something is sleeping, we're going to run. If there is nothing ready, we're going to do deadline pop something off the heap. This is the same as in the code before. We're going to figure out how long there is between the deadline and now. And if the delta is greater than 0, we're going to do a sleep. And then after we've done the sleep, we'll put the coroutine on the ready queue. That code is almost virtually identical to the previous code with callback. Okay, so you have like a little sleep method there. To actually do the sleep, we have to use the scheduler basically. So instead of saying time sleep, we would say await schedule sleep. Like that. We don't need to switch tasks anymore because that's taken care of in the sleep. Okay, so like let's say I just said await schedule sleep, like that. That sleeping call should automatically take care of the task switching because it like if you remember the sleep method, it's already doing the switch there. All right, let's try this out. Let's see if it actually works here. Time sleep. Oh yeah, okay. I guess it would help if you actually put the delay time there. Okay, so you see it going down and now up 1, 2, 3, and then down and yeah. I guess if I run it for longer here, count up 20 or something, you'll see it kind of alternating kind of more here. So. Kind of a neat little magic trick that has taken place. I think the important thing about it is that again the code that you're writing does not involve callback functions. Like this countdown and count up. Those basically look the same as the original code. Like here is the kind of the original formulation of those. Like that. It virtually looks the same. The only difference is that you've declared these as async functions. They're using the await statement to do the sleep, but otherwise it's exactly the same kind of same control flow. That's actually a big appeal of async await, is the fact that you can, that you can use the same kind of control flow like that. Very, very kind of interesting. Okay, so that's the first part of it. Also, actually, the implementation of sleep is also fairly straightforward. I mean, maybe it's a little bit sneaky, but I mean, essentially, it's like you figure out what your deadline is. You put yourself onto this sleeping queue. The self current is like you, right? It's like current represents like the current thing that's running. So you put that on the queue, and then you sort of just take yourself out of commission, if you will. In some sense, you're pulling kind of like a disappearing act. It's like you're, by setting current to none, you're basically saying, hey, I need to disappear for a while. I'm going to sleep. I'm disappearing. So I'm going to disappear, and then when I do the await switch, the scheduler will switch to another task. And again, that switch does that by executing that yield statement. The yield essentially makes the thing switch. So again, kind of a neat little magic trick there. Now we're going to do the same thing that we did for the last code. I mean, one of the problems that we looked at after that was how to do this like producer-consumer problem. I don't know whether you remember the producer-consumer problem here. This is the threaded version of the producer-consumer problem. What I wanted to do is actually take a look at this with the yield statement, basically with async await. So we're going to do the same kind of formulation that we did before. So we're going to have async await. We're not allowed to use any of this stuff, like none of the queue or threading or time or anything like that. So what we're going to use is essentially the same scheduler that we had before. Okay, so we're going to have our scheduler, async sleep, new task, run, and so forth. It's going to sit in the background, and what we're going to do is kind of formulate what we need to do to make this like producer-consumer problem work. Okay, so like what is going to happen here? Well, the first thing that's going to happen is these things need to become async function. And things like the sleep, we're going to use like await schedule sleep. This is what we did in the last part, like just a second ago. Okay, so we're going to turn these things into async functions. And the next thing that we're going to do is we're going to implement kind of a queue that involves those. I guess I called it async queue. So we're going to have our queue object. In here, you're going to have your items. Okay, so this is the same thing as before. We had a waiting deck as well. And what we're going to do is kind of the same trick as before. So like we have a put method where you have an item, so that's going to put something into the items deck. We're going to have a get method which basically waits for an item. So if not self items, we basically have to wait. We'll get around to how that's going to work in a second. And then if there are items, we basically pop one of them off. Okay, so we're going to return an item there. So this is the structure of how we want this to work. Now the question is, how do we make the wait work? Well, the whole idea on the wait is that we need to suspend ourselves by using that waiting queue. Okay, so like this is the same thing that we did before. So the way that you're going to wait is you're basically going to append yourself into that waiting area. You're basically putting yourself to sleep. or putting myself to sleep. Okay, so I'm gonna put myself in there. I'm then going to go to the scheduler and basically again pull this kind of disappearing act again. Okay, so this is this disappear from the scene for the moment, and then once I've disappeared from the scene, I have to do this like task switch, right? Like that. So it looks very similar to the sleep before. Basically, it like if there's no items, I'm going to put myself in kind of the waiting area. I'll set the scheduler current to none. I'll do a switch and then I'll pull a disappearing act, and then I just forget about it. I'm actually done with that. In order to use await, this has to be an async method. And what's going to happen up here? Let's say you have a put method. This thing is basically going to look at the waiting. Like if there's something waiting, then what we would need to do is go to the scheduler and we would say, okay, well, if there's something ready, if something was waiting, I need to append the thing that was waiting. Okay, I would do that. Then again, kind of mirroring the previous code. And here's what you can do to make that work. I mean, essentially, you're going to keep all the code the same here. Put n, await, schedule, sleep, await, queue. The big difference is that the get now has an await attached to it. Okay, let's make the queue. What we will do is add some tasks. Okay, so we're going to make a new task, producer, Q10. Make a consumer like that. If this is working, you should see the producer kind of feeding the consumer. Now let's try it out. I think I called that Y producer. Coroutine producer was never awaited. Let's see. Let's see what's going on there. Schedule new task. Oh, you have to run it. Okay. If you don't run it, then strange things happen. All right, we see the thing work. Personally, I feel like the code is maybe a little bit easier to understand. I mean, definitely the user code here of writing the producer and the consumer is a lot simpler. We're not using callback functions. We're not having to do all this scheduling of callbacks. It essentially looks exactly the same as the thread code. I mean, here's kind of the threaded version of that. We kind of line it up here. You find that the code essentially just lines up the same. It's exactly the same. It's just that certain functions have an await on it where they did not have an await before. Kind of interesting there. One thing that is maybe a little strange about the design is there's a little bit of an asymmetry between the get and the put. Like get needs an await attached to it, and put does not. As far as kind of like a design element of that, it might make sense to make the put also an async function. That would just kind of make the API maybe a little bit more symmetrical, if you will. Okay, so like when working with the queue, you would use await for both the put and the get. I think that's probably like a good idea to do that. Just because it would be very easy to kind of miss the await or to like keeping track of which one has it and which one doesn't. I think it would make sense to just make it very uniform. It's like, okay, for this queue, you always use await for both the put and the get. And the get method, pretty, you know, I think it's pretty straightforward. It's like if there's no items, you put the current thing to sleep, and then you switch to another task. And then magically you will awaken when some items become available. So like this whole thing here is basically going to make the get kind of wake up if there's something happening. So that's kind of nice. And really you're really seeing some of the appeal of using the async and await, and that it actually, I think the implementation is in sort of simpler to explain in some sense. Now, the other thing that I did with this queue, okay, kind of the final thing with the queue here, is we had this modification where we had the closed, like the little closed flag. I don't know whether you remember that or not, but I had this idea of a queue where you could close it. Could set closed there. Set close queue, and then we had some error checking kind of put into the thing as well. So if self closed, raise queue closed, and then we had this whole thing in the get where we want to raise like an exception, basically. Like if there's no items, then we might want to check like if the queue is closed, something like that. So if there's no items and the thing happens to be closed, we will raise that. One of the complexities that we had in the previous code actually concerned this whole error handling stuff. I don't know whether you remember that, but with the callback-based approach, we ended up having to do this really convoluted trick of packaging the exception and the value into this result object and trying to carry like both results around and dealing with that. It turns out that we don't really need to do that here. Now it turns out that this is actually enough. We can say, like if the thing is closed, we'll just raise the exception. Actually, there is one little thing that I'm going to put in here. You might want to make this like a while loop. I'll explain why in a second, but it's like while there's no items, if the queue is closed, we'll raise the queue closed. Otherwise, we'll suspend ourselves. The way that the reason that you might want to do that is that this closed thing, if there happen to be things waiting, and there was nothing items there, I basically want to reschedule things. So I'm gonna do like a little reschedule thing. What's gonna happen with that is they will basically wake up after the switch, and then they'll go back around and find out, oh, there are no items, but then they'll pick up the fact that it's been closed. It's a little subtle, but we can put that error handling in there. And then it turns out that we can use the close method. Okay, queue close, producer done. Here, I would just maybe wrap the whole thing with like an exception block or something, like while true, get the item, consume it, and then just catch like that queue close thing. Okay, let's see if that works. I called that Y producer 2. Okay, so see the thing running. Again, the idea on the close is that something that would like shut down the queue, and then do it in kind of a nice, graceful way like that. So you see the thing working. I don't know what you make of that. I think the code is a lot cleaner for that. I mean, essentially, you just raise like normal errors. You don't have to package them into this kind of like magic result object or a future or anything like that. And that is actually another kind of feature of async await, is that it solves a lot of problems related to just the overall control flow of the program, but also just the way that results are communicated in that control flow. It appears much more like just straight sequential code. You can raise exceptions, you can return values. You don't have to like sort of package things up in a really strange way. Okay, so that is kind of a really nice sort of feature of that. So one of the challenges in building an async library is actually knowing which one of these approaches to take. Basically, we've seen two different approaches for implementing one of these libraries. You have the approach involving coroutine. This is where you're driving things as a generator. But you have this other approach, which was, calling code, using callback functions. So we have like the approach using callback functions instead. And, there's this question of like, which one of those do you use? Do you have to pick one or the other? Or can you use both? I mean, that's maybe the more, kind of extreme case. And maybe you want both of these programming models available. So the final problem that I thought we would look at is actually how you would make coroutines work on top of a callback-based scheduler. This is going to be a little strange, but essentially what I'm going to do is I'm going to take all this like coroutine stuff with the awaitable and the switch and the async queue and stuff, and pose this question: what if you had to run it on top of like a scheduler that used callback functions? Okay, so this is the sort of the callback based scheduler here from earlier. So it's going to have the queue, it's going to have sleeping, sequence, call soon, call later, and run. And I'm going to try to basically like layer the async await on top of that. Now let me just tell you why I'm doing this. It turns out that async IO is basically following this model. One of the complexities of async IO is that it supports both callback-based programming and coroutine-based programming at the same time. So it's trying to be, kind of all things to all people in some sense. The way that it does that is that at a very low level, it is built entirely around the concept of callback functions. So it is using a kind of a scheduler that uses callbacks. Okay, so we have callback functions like that. But to make coroutines work, and again, coroutines meaning like the await async syntax, they are essentially using like a little adapter trick. I mean, here's kind of the gist of the idea. What they do is they make like a wrapper class. You make a class task. And you can make this task kind of wrap around a coroutine. Okay, so this is like a kind of a wrapped coroutine. And what they do with this wrapped coroutine is they basically fake the programming interface of a callback function. So what they do is they make it look like a callback. And the way they do that is they essentially put a call method on here. You're like, okay, this is kind of interesting. Okay, so you're gonna do like a try call. So when you call the thing, what you will do is you will basically drive the coroutine. using kind of the original technique, and then you will catch a stop iteration and pass. The other thing that you might do is build up, some of the same code from that we had earlier. I mean, essentially, maybe what you would do is you would, in the task, you would take the scheduler, you would set the current running thing to myself. You'd set the coroutine, you do the send like that, and then if the scheduler current is still set, you'd append yourself there. Okay, so this code here, this is kind of driving the coroutine kind of as before, but the callback part of it is basically making it look like a callback up here. Okay, so you've got this really kind of strange, kind of wrapped coroutine object, and then what you would do is basically kind of fake an interface for that. Okay, so if you wanted to have like a new task method on here, this is on your scheduler, you would provide it with a coroutine, and what would happen is you would basically append a task wrapped around the coroutine. Okay, so again, this is kind of your wrapped coroutine here. Okay, so you make a new task, you wrap it up like that. If you wanted to have functions for sleeping and other things, you could put like an async def sleep method on here, like that, and delay. And the way that you would do this is you would kind of fake, what you did before. Okay, so if you wanted to sleep with a delay, what you would do is you would basically take you would basically say, okay, self call later delay self.current. Keep in mind, call later, that's that thing that you wrote earlier. That's the callback-based function. Okay, so what you're going to do is you're going to say call later self.current. Self.current is this task object, okay? That's the task object. It looks like a callback function because it has a call method. Okay, so you're going to call later on that. You would then set the current to be none, right like that, and then you would await the switch function. It might seem kind of wild, but I mean, essentially what's going to happen is that this is the same technique as we had before. It's just that we were kind of wrapping things with a callback function, and then we've got this thing driving the coroutine. If we've done that, I'm pretty sure that this ProducerConsumer code will still run the same way that it did before. I mean, we'll have like the new task producer, new task consumer, and so forth. Let's see if it still works here. Scheduler, new task. Let me see what we got here. Make sure that I scheduler, new task. Oh, I might have. Okay, I think I might have a indentation problem on that. Okay. Yes. Okay. Slight technical thing. Okay, so you see the thing running. Okay, it's kind of the same code as before. So you see the thing working, but this new version should be able to also do callback functions. So if I were to like I could take like my callback functions from before, like the countdown and the count up thing. Let me take those. And also put those in my code. So I'm gonna have count up, count down. this is the callback-based thing. Okay, so we've got callback functions. If we add those and we run the code, we should see everything kind of going at once. We see down and up and consuming and so forth. So you've got like basically both programming models kind of executing at the same time. And the thing that's making that work is the fact that you've got kind of this extra layer that is adapting coroutines into callback functions. That can actually make some of the code extremely difficult to figure out because you have a mix of code that's using callbacks and you have a mix of code that's using async await. And this kind of thing actually this is a big reason why it can be very hard to kind of understand like the internals of async IO, because it's doing something very similar to this. If you read the docs for async IO, it talks about, you know, tasks wrapping coroutines and futures and callbacks and all this stuff. And it can make your head kind of spin trying to make sense of it. But that's what it's doing, is actually trying to support both of these programming models, basically supporting both callbacks and coroutines. All right, the final thing I want to talk about is how things like I/O handling and other features get built into like an async framework. So as you'll notice so far, basically we've built, you know, kind of a scheduler that can, you know, schedule functions and so forth. We've built this queuing object, you know, that basically let tasks put and get things on a queue. And one of the things that you'll notice is that the implementation is basically very similar between all of these things. And the implementation usually relies on some kind of waiting area, like a waiting area for tasks, or things like, you know, like the sleeping area up here in the scheduler. And what you're doing is you're essentially setting things aside to execute later. And that general principle applies actually for everything that you might do in one of these, you know, async framework. So just as an idea, or as a, you know, as an example of that, you could start adding functions for like I/O handling. Like what are the I/O events that happen on like a socket or something? Well, I mean, one of the one event that actually happens is you might want to like wait for reading, for instance, like read wait, where you give it like a file number and then a callback. So the idea here is, you know, maybe you trigger function when file number is readable. This is kind of the idea. So the way that you might do that is you would sort of set up like a little waiting area, like, you know, read waiting is maybe a dictionary or something. And what your read wait would do is it would kind of put that function in the read waiting part. And maybe you do the same thing for like a write wait or something. You'd have write wait, same file number func. Again, trigger function when file number is, you know, writable. And you would do the you know, same kind of thing. Okay, so you're basically taking a function, you're kind of setting it aside for later use. Okay, so you have write waiting is dictionary as well. So part of what you need to do is you have to have like these waiting areas. The second thing that you need to do is you have to have some way to get functions out of those waiting areas. So that is what was happening here, like with the code for sleeping. There's a bit of code that kind of, you know, looks at like the, you know, the sleep queue and, you know, pops things out and puts it back on the ready queue. We would have to have something similar for that for our I/O function. Okay, so you have to have a similar idea. It turns out that one of the functions for doing that is the select function from the select module. Not really going to do a big tutorial on that, but select is a function that lets you monitor I/O, like I/O devices, I/O ports, and file numbers and so forth. And so maybe what you would do in your little scheduler here is you would modify the run loop. You'd sort of say, okay, while there's something ready or sleeping or read waiting or or right waiting. Okay, so we're kind of checking all the different queues we're gonna spin. If there is nothing ready to run, then what we're gonna do is we're gonna wait for something to happen. Now, one tricky thing is it turns out that sleeping and I/O are often like mingled together. Usually, what might happen is you would do like an I/O select with a timeout, basically. So what you would do is you would sort of say, well, okay, if there's something sleeping, we're going to look at the kind of the topmost thing, which is always in the position 0 there. Okay, so we're going to get the deadline from the topmost thing that's sleeping, and then we're going to use that to set like a timeout value. Okay, so timeout is going to be deadline minus time. Okay, so if timeout is less than 0, we're going to set it to 0. Okay, so we're going to do that. And then if there is nothing sleeping, we would set the timeout to none, like that. Okay, so this is kind of a wait forever kind of idea. And then what we're gonna do is sort of use the select call. And then we're going to wait for I/O. Okay, so it's admittedly a little bit complicated, but you've got like two different things kind of going on there at the same time. You've got like both a waiting for I/O and a kind of sleeping kind of feature at the same time, and sleep there. So you're going to wait for I/O. Anything that comes back for that. So file descriptor in can read, we will move something to the ready queue for that. Okay, self ready append self read waiting pop fd. Okay, so we're gonna do that. And then we're gonna do the same thing for can write. And then we will finally check for sleeping. Okay, so check for sleeping tasks. The way that that's going to work is we would basically figure out like what time it is right now, and then we would see whether we can pop things off the sleep queue. So while self.sleeping, like this, if now is greater than self sleeping 0, 0. That's basically the deadline. What we do is append the final thing there. Okay, that's a little bit ugly there. We're essentially putting the function back on the sleep queue there. If the deadline is not passed, then we'll just like break out of there. Okay, so we're essentially again kind of moving tasks around. We would have this sort of read wait, write wait kind of thing for I/O handling. Now, we might provide like different, like nicer kind of helper functions to kind of interact with that as well. So like if I wanted to make this nice for use with coroutines, for instance, I might put something, I might write like sort of async functions to make that work. So you might do something like, async def, I don't know. Like let's say I wanted to like wait for something to happen. Okay, I have it read wait, write wait. Well, I don't know. Let's just make something like for like a socket or something. This is kind of like a simple example. Like read something on a socket. Maybe what I might do is write a function like this, where I would basically do a self like read wait on socket, and then the callback would basically be me. like make the current task. I would set the current to none. I would do an await switch. Okay, I'm following the model of the sleep above here. Okay, wait switch, and then when I come back, I would do a socket receive like max blade. Here's kind of the theory on how this is going to work. It's basically if I want to read from a socket, I would wait until something is there, and then while I'm waiting, I kind of switch to something else, and then I return, and then I would do the same thing for maybe like a send or something. I'm not sure I'm super happy about this interface here, but you'd do a write wait. Again, you do the switch, a wait there, and then return like socket send or something like that. Again, I don't know whether I'm like super happy with that, but I don't know. Let's do one other method here, and then we'll write like a little bit of code to see if it works. Okay, so maybe you have that. Here's what it would look like to do that. Maybe I would write like a little server or something like that. Like here's a TCP server on some address. Let's import the socket module. So we'd make a socket, bind it to some address, listen on that on that address, and then go into some loop, and then get a connection. So we would do an await, like schedule accept socket, like that. Maybe we would, like once we get that, we would schedule a new task, echo handler or something. Yeah, there's like part of the network code, and then maybe we would have like an echo handler socket like this, where we end up in a little loop like this, and we would basically say, okay, data is going to be await scheduler receive, where we give it the socket and like some data, not data break. I'm just going to echo it back with little message there. Okay, scheduler send socket, and print connection close. Okay, this is this kind of classic echo server kind of thing, and then maybe maybe we add these to our to our thing here. New task TCP server port 30,000 or something, and then run the thing. So if we've done that right, you'll find that you can do maybe do some I/O on it. Admittedly, that's a little bit a lot to like throw at you at the end here. But let's run it, see what happens here. I think that was Y producer 4. Okay, so the thing is running. If that's working. Oh, cannot use an already awaited coroutine. Oh, that's kind of an interesting. An already awaited. It's okay, interesting. Yeah, maybe have a. Let me take a look at what we've got going on there. Probably have some strange thing here. Let me take out that TCP code just to make sure that it's not that. Oh, nice. Okay, consumer. Okay, maybe it's something with the consumer done thing here. Let me vitamins none break print. It's basically not getting that. Schedule current switch. Concurrent. Huh. Yeah. Well, I don't know. Well, let's try. I'm not sure what that is. Maybe instead, let me just try running the TCP server here, and I will turn off the producer consumer thing. It's like there could be a bug in that. Okay, got that running. If the other thing is working, what we should be able to do is actually go into another window and then connect to that, and then see it really like you're responding. Okay, so the I/O thing is looks like it's actually kind of working there. Connection closed. Oh, I think I forgot to close the socket in there. Okay, so it's okay. Few little glitches on that, but that is kind of the general idea. There is that kind of wild, but that's this is sort of the core of these async frameworks. You often have like a mix. A mix of callback functions. You have a mix of coroutines. There's often kind of scheduling and other things going on, and they might all be mixed together in some way, and that is often a very kind of interesting, head exploding way to code there. So I think that's all I'm gonna say about that. I'd like to figure out why the queue thing is not working, but I'm not sure I see it at this point in the workshop, and I'm not even sure it's all that critical. I'll take another like sort of quick tour through the thing just to see if I see anything obvious, but I don't off the top of. Actually, I found the bug in the code. It's this extra append up here. I should have deleted that. So there was a delete in the sleep where I was getting something on the queue more than once. So if you do that, it should fix that. We should get rid of that. We get rid of the error where it was like, trying to do something, and then we should have the network code should still work here. All right, so that's what that was. Okay, well, I'm not going to worry about that. So thanks for listening to this. Hopefully this was kind of interesting. I will try to post the code online, so should be a link with the video that goes along with this. So all right, thanks everyone who came to the workshop.